the problem is solve the recurrence relation an minus 2 an minus 1 plus an minus 2 is equal to 2 with initial conditions a0 is equal to 25 and a1 is equal to 16. Okay. So the given non-homogeneous recurrence relation is, so this is non-homogeneous recurrence relation. Here constant is exist. So an minus 2 an minus 1 plus an minus 2 is equal to 2. So the complete solution of this given non-homogeneous recurrence relation is sum of homogeneous solution and particular solution. First we find homogeneous solution. So the associated homogeneous equation for given non-homogeneous equation is an minus 2 an minus 1 plus an minus 2 is equal to 0. So the degree of this given homogeneous equation is 2. So next we write characteristic equation for this homogeneous equation, that is r square minus 2r plus 1 is equal to 0. Okay, r square minus 2r plus 1 is equal to 0. So the roots of this equation is, this is of the form a minus b whole square. So r minus 1 whole square is equal to 0. R is equal to 1 comma 1. So the roots are real and same. So the solution of homogeneous solution is an of h is equal to c1 plus c2 n into 1 power n. This is homogeneous solution. Okay. So let it be equation 1. So next we have to find particular solution. Since RHS of the recurrence relation is 2, RHS of the recurrence relation is 2 and it is a constant, we assume the particular solution for this constant term. So RHS term అనేది కాన్స్టెంట్ అయినప్పుడు పర్టికులర్ సొల్యూషన్ ఏంటి అండి d. So an of p is equal to d is a constant. So now it satisfies the given non-homogeneous equation. Then we put an of p value in given equation. So in place of an, d minus 2d plus d, that is equal to 2. So here 2d minus 2d, this value is equal to 0 is equal to 2. So our assumption is wrong. So which is impossible. So thus our assumption is wrong. So next we have to consider another solution for this equation. Now we assume that an of p is equal to nd. An of p is equal to nd. So using this solution in the given recurrence relation, we get in place of an we substitute nd minus 2 into n minus 1. So given equation is 2 an minus 1. So an value nd. So then an minus 1 value is equal to n minus 1 into d. Using this solution, we write 2 into n minus 1 d plus n minus 2 into d is equal to 2. We simplify this equation, we get nd minus 2nd plus nd plus 2d minus 2d. So this value is equal to 0 is equal to 2. So here also our assumption is wrong. So which is impossible. So 0 is not equal to 2, but here it is given 0 is equal to 2. So our assumption, the solution nd is wrong. So we go for another assumption, that is ak of h is equal to n square d, not h, p. It is p here. So we consider particular solution an of p is equal to n square d. So using this solution in the given recurrence relation, we get in place of an n square d, in place of an minus 1 n minus 1 whole square d, n minus 2 whole square d is equal to 2. We expand this expansions by using a minus b whole square formula. So 2 into n square minus 2n plus 1 into d plus n square minus 4n plus 4 into d is equal to 2. Okay, we simplify these expansion, n square minus 2n square d plus 4nd plus 4nd and minus 4nd cancel. Next, here this is n square d, here d missing. Okay, n square d minus 2n square d minus into minus plus 4nd minus 2d plus n square d minus 4nd plus 4d is equal to 2. So total n square d plus n square d 2n square d minus 2n square d cancel, remaining minus 2d plus 4d. 2d is equal to 2. So from that d is equal to 1. So the solution of particular solution is n square is d. Okay, so now we substitute d value in this solution, we get particular solution an of p is equal to n square. An of p is equal to n square. Hence the general solution, complete solution of given equation is sum of homogeneous solution and particular solution. What is homogeneous solution? C1 plus C2n into 1 power n plus n square. So n square is the particular solution. Now we have to find C1 value and C2 value using given initial conditions. Okay, so the given initial conditions are a naught is equal to 25, a1 is equal to 16. So now we put n is equal to 0 in this equation. We get a naught is equal to C1 plus C2 into 0, 0, 1 power 0, 1 plus 0. So C1 is equal to 25. Okay. So next we put n is equal to 1 in equation 1. A1 is equal to 16. So C1 plus C2 plus 1 square is equal to 16. So we know the C1 value, that is 25. We substitute that value. We get C2 is equal to minus 10. So now we substitute C1 and C2 value in equation, we get the complete solution of the non-homogeneous recurrence relation, that is an is equal to n square minus 10n plus 25. This is the complete required solution of a given non-homogeneous equation. Okay. So in this way, we solve a given non-homogeneous recurrence relation. Okay. Another formula, another problem, solve the recurrence relation AK minus 7 AK minus 1 plus 10 AK minus 2 is equal to 6 plus 8K with initial conditions A naught is equal to 1, A1 is equal to 2. A naught is equal to 1 and A1 is equal to 2. This can also be asked like S of K minus 7S into K minus 1 plus 10 S of K minus 2 is equal to 6 plus 8K. So here S of 0 is equal to 1, S of 1 is equal to 2. Okay. So the given non-homogeneous recurrence relation is AK minus 7 AK minus 1 plus 10 AK minus 2 is equal to 6 plus 8K. So here RHS term is C0 plus C1K form. Okay. 6 plus 8K. So first we write a homogeneous solution for given equation. We consider homogeneous equation from given non-homogeneous equation, that is AK minus 7 AK minus 1 plus 10 AK minus 2 is equal to 0. So the degree of this equation is 2. So its characteristic equation is R square minus 7R plus 10 is equal to 0. So we have to find roots of this equation. So the roots are r minus 5 into r minus 2 is equal to 0, r is equal to 2 comma 5. These are real and distinct roots. The homogeneous solution is ak of h is equal to c1 2 power k plus c2 5 power k. This is homogeneous solution for given recurrence relation. Okay. After that, we have to find particular solution of given non-homogeneous equation. That is, we need to find the particular solution. So the RHS term is of the form C0 plus C1n. So first degree polynomial. So the particular solution is D0 plus D1k. D0 plus D1k. So it satisfies the given equation. We substitute this value in given equation. So in place of a n ak, d0 plus d1k. In place of ak minus 1, d0 plus d1 into k minus 1. In place of ak minus 2, d0 plus d1 into k minus 2 is equal to 6 plus 8k. Okay, we simplify this expansion. D naught minus we 7 D naught plus 10 D naught plus D1 K terms D1 K minus 7 into K minus 1 plus 10 into K minus 2 is equal to 6 plus 8K. So total 11 D naught minus 7 D naught is equal to 4 D naught plus D1 into K minus 7K plus 10K. So 11K minus 10K plus K 11K 11K minus 7K 4K. Okay, 4K. So here remaining values 4D naught minus 13D1 plus 4D1K is equal to 6 plus 8K. So equating the corresponding coefficients on both sides. So 4D naught minus 13D1 is equal to 6 and 4D1 is equal to 8. From that D1 is equal to 2. From that D1 is equal to D1 is equal to 2 and we substitute D1 value, we get D naught is equal to 8. So the particular solution AK of P is equal to A 8 plus 2K. D naught value 8 and D1 value 2. So the particular solution is 8 plus 2K. So the complete solution of given recurrence relation is sum of homogeneous relation homogeneous equation and particular solution, that is AK is equal to C1 2 power k plus C2 5 power k plus 8 plus 2k. So now we have to eliminate arbitrary constants of this equation, that is C1 and C2. We have to find C1 C2 values using given initial conditions A0 is equal to 1 and A1 is equal to 2. Now we put and k is equal to 0 in equation 1, we get the equation C1 plus C2 plus 8 is equal to 1. From that C1 plus C2 is equal to minus 7. Okay. So next we put and k is equal to 1. We get the equation C1 2C1 plus 5C2 plus is equal to minus 8. Okay. Solving these two equations, we get C1 is equal to minus 9 and C2 is equal to 2. C1 is equal to minus 9 and C2 is equal to 2. So the required solution is we substitute the C1 and C2 value in equation 1. We get the complete solution of given non-homogeneous equation, that is AK is equal to minus 9 2 power k plus 2 into 5 power k plus 8 plus 2k. This is the required complete solution of given non-homogeneous recurrence relation. Okay. So next problem. Solve the recurrence relation an is equal to a 4an minus 1 minus 4an minus 2 plus n plus 1 into 2 power n. Okay. So the RHS term of the given recurrence relation is n plus 1 into 2 power n. So the first we find homogeneous solution. For that we consider homogeneous equation for given non-homogeneous equation, that is an minus 4an minus 1 plus 4an minus 2 is equal to 0. So this with the degree 2. So next we write characteristic equation of this equation, r square minus 4r plus 4 is equal to 0. So this is, we solve this equation, we get the roots r is equal to 2 comma 2. So the homogeneous solution is, these are real and same roots. These are real and same roots. So what is the solution of homogeneous? C1 plus C2 n into r power n. So here r value is 2. So The solution is C1 plus C2n into 2 power n is the homogeneous solution of given recurrence relation. Okay. So next we have to find particular solution. So RHS of the particular solution is of the form n plus 1 into 2 power n. Here R value is equal to root of the characteristic roots. Okay. So how many times? 2 times. So we assume the particular solution to be, this is C1 plus C2 n into n square 2 power n. Okay. C1 plus C2 n into n square 2 power n. This is the particular solution for given non-homogeneous recurrence relation. We substitute this value in given recurrence relation. So C1 plus C2 n into n square 2 power n minus 4 into C1 plus C2 into n minus 1 into n minus 1 whole square 2 power n minus 1 plus 4 into C1 plus C2 into n minus 2 whole square 2 power n minus 2 is equal to n plus 1 whole square, sorry, n plus 1 into 2 power n. Okay. So we simplify this equation, we get 4 into C1 plus C2 n into n square minus 8 into n minus 1 whole square into C1 plus C2 into n minus 1 plus 4 into n minus 2 whole square. So common terms C1 plus C2 into n minus 2, that is equal to 4 into n plus 1. Okay. So from this we get, put n is equal to 0, we get minus 8 into C1 minus C2 plus 16 into C1 plus 2C2 is equal to 4. So from this we get the equation C1 minus 3C2 is equal to 1 by 2. So equating the coefficients of n on both sides, 16C1 minus 16C2 minus 8C2 minus 16C1 plus 32C2 plus 16C2 is equal to 4. So 24C2 is equal to 4. From that C2 is equal to 1 by 6. So we just simplify this whole term. We get C1, C2 value. C2 is equal to 1 by 6. From that we find C1 value 1 by 2 plus 1 by 2, that is equal to 1. So the particular solution, we substitute these values in particular solution. The particular solution is C1 plus C2 n into n square 2 power n. So 1 plus 1 by 6 into n square 2 power n, we multiply this, we get n square plus n cube by 6 into 2 power n. So the general solution of the recurrence relation is sum of homogeneous solution plus particular solution. The homogeneous solution is C1 plus C2n plus n square plus n cube by 6 into 2 power n. Okay, this is the complete solution of given non-homogeneous recurrence relation. So first we find homogeneous solution, after that we find particular solution. Particular solution is based on RHS term of the given equation. Okay, next one, similar problem. Solve the recurrence relation an is equal to 4an minus 1 minus 4an minus 2 plus 3n plus 2 power n with initial conditions a naught is equal to 1 and a1 is equal to 1. Okay. So the given recurrence relation is an minus 4an minus 1 minus 4an minus 2 is equal to 3n plus 2 power n. So from that we write homogeneous equation an minus 4an minus 1 minus 4an minus 2 is equal to 0. So the characteristic equation is, the degree of this equation is 2. From that we write characteristic equation r square minus 4r plus 4. Sorry, here plus 4. Okay. So the roots are r is equal to 2 comma 2. Thus the homogeneous solution is an of h is equal to c1 plus c2n into 2 power n, because here roots are real and same, then the solution is c1 plus c2n into 2 power n. So RHS term is equal to 3n plus 2 power n. So this is polynomial and this is r power n form. So here we exist two cases of particular solution, an of p1, an of p2. The solution for an of p1 is d0 plus d1n, and the solution for an of p2 is r power n form. So first we find solution for an of p1, that is d0 plus d1n, because 3n can be written 0 plus 3n. So this is of the form c0 plus c1n form. Okay, so this is 0. 0 plus 3n form. So this means c0 plus c1n form. So the solution is d0 plus d1k. So the particular solution 1 is d0 plus d1n. We substitute this solution in given equation. We get d1 value 3. We solve this total value. We get d1 is equal to 3. Equating the constant terms on the both sides, we get d0 minus 4d1 is equal to 0. From that, we get d0 is equal to 12. We substitute d0 d1 value in particular solution. So an of p1 is equal to 12 plus 3n. So next we have to find particular solution 2, that is RHS term 2 power n. Here RHS term, in this RHS term, r value is equal to double root of the characteristic equation. So the solution is dn square 2 power n. So double root of the characteristic equation. So here r value is equal to 2 times equal to characteristic equation. So characteristic roots. So the solution is dn square 2 power n. We substitute this particular solution in given equation. We get d value, that is d is equal to 1 by 2. So dn square 2 power n minus 4d n minus 1 whole square 2 power n minus 1 plus 4d into n minus 2 whole square 2 power n minus 2 is equal to 2 power n. So we solve and simplify this. We get d is equal to 1 by 2. Okay. Therefore, the particular solution corresponding to 2 power n is 1 by 2 n square 2 power n. So total particular solution is sum of particular solution 1 and particular solution 2. So we get particular solution 1 12 plus 3n, and the particular solution 2 is n square 2 power n by 2. This can be written 2 power n minus 1. So complete solution of given non-homogeneous equation is sum of homogeneous equation and particular solution. So from this solution, we eliminate these arbitrary constant using given initial conditions. So the given initial conditions are a0 is equal to 1 and a1 is equal to 1. Okay. So we put n is equal to 0 in this equation. We get c1 plus 12 is equal to 1. From that, c1 is equal to minus 11. So c1 is equal to minus 11, and put n is equal to 1. And put n is equal to 1, a1 is equal to minus 1, and the equation 2c1 plus 2c2 is equal to minus 18. So we substitute c1 value, we get c2 is equal to 2. So we substitute c1 and c2 values in this solution. We get the complete solution of given non-homogeneous equation, that is an is equal to, what is c1 value? Minus 11. So minus 11 plus 2n into 2 power n plus 12 plus 3n plus n square 2 power n minus 1 is the required complete solution of the given non-homogeneous equation. Okay.